like to thank the organizers for the opportunity to speak about this work here. I also should apologize maybe because the work is not kind of on the mainstream questions of the conference, but I would still argue that it's somehow connected to the general discussions of quantum statistical mechanics, in particular in connection to establishing quantum ergodicity in simple models of interacting systems. But the talk is essentially about the questions of quantum chaos, which is more like fundamental problems of, let's say, quantum statistical mechanics. So I should first do a little bit of, let me first mention, this is basically about some very new work that we have done. Nothing is yet published. There are 2 papers on the archive, which I will quote. The collaborators are postdoc Bruno Bertini and 2 PhD students, Pavel and Marco. So I should first start with some very gentle introduction into quantum chaos, which has been developed many years ago. And one of the organizers here is Giulio Casati, is one of the pioneers of this problem. So, this problem has been essentially solved, not quite, but essentially solved for single particle systems. Now, the problem has been around, and there are many people who didn't even appreciate the problem, but they got used to it so much that they didn't appreciate that there is a problem. But there is a problem for many body systems. And this is what I'm trying to convince you. And also I try to show there is a path to the solution of this problem. So first of all, what is the problem? And the problem is very simple. You have this random matrix theory, which I'm sure you heard about, and some of you have actually used it, which basically describes some universal features of non-integrable systems, simple non-integrable systems, typically of many constituent particles like nuclei. These are experimental data. And this is Wigner's surmise, which nicely explains distribution of level spacings. But it has been found in the 80s, in particular by these pioneering papers by Giulio and Berry, and then it was this most famous PRL of Bochigas, Giannoni, and Schmidt, which basically launched the conjectures, sometimes called quantum chaos conjecture, which states that even very simple models with chaotic classical dynamics should conform to random matrix theory. So the spectra should be described by random matrices. So these models, this is an example of such models, is the Stadio and Billiard, is a one-particle problem. The only universal feature it has is it's strongly chaotic. Any trajectory basically is unstable. So these models, this type of models, for some category of models like this, it has been shown later. In particular, there's been kind of very slow but progress, starting with paper by Berry and then ended in the papers by the group of Fritz Hacke in 2004, 2005. And these papers basically established why, basically they found physical mechanism why one has random matrix theory, which is a which is a basically zero parameter theory. Why this theory is successful to describe models with a lot of physical structure. So the RMT is a structuralist theory, but the models that it describes are models with a classical limit with definite deterministic trajectories, which are chaotic, but still, how can these trajectories be connected to, how can one wash away all the dynamical information and end up with a completely universal model with 0 parameters? Yeah? And also the important question is, where is the border between, having random matrix description and models which violate random matrix description, which are not, let's say, quantum chaotic? In semi-classical systems, this has been understood and has been related to strong dynamical chaos. Yeah? And the key underlying concept is periodic orbit theory. So there is again a tool which has been developed starting from Gutzwiller in the end of 60s and then later developed in the 1980s and 1990s, which basically nicely connects a spectral density and sums over classical periodic orbits. Yeah? And this has been used for the first time in 1985 by Berry to show that the spectral two-point correlation function has to be described, at least the main features of it has to be described by classical periodic orbits. Then, I'm just giving you this as an introduction, but be careful, because I will discuss systems where there are no classical periodic orbits. But I try to find a substitute concept, a concept which can be used instead of that. There should be some sort of recurrent, structures on which, periodic orbits are nice because they provide kind of recurrent structures in quantum conservative, that is unitary dynamics, on which you can sit. So now the key question for my talk will be, what are the corresponding structures in quantum many-body systems? But let me just let me just conclude this slide just to show you how it goes. So the key object that people are interested in, and we will be interested, is this two-point correlation function of the spectrum. So it's the simplest kind of non-trivial object. So you have a spectral density, rho of E, and then you compute the correlation function when you average over the position of the energy. For example, think of a system which has finite energy, I mean like spin system, finite energy range, and then you can average over energy range. And then you basically have this parameter epsilon, which is the energy distance, and then you scale it with respect to mean level spacing. So the key, I mean, there is no basically energy scale in this object. It's dimensionless. And then you do the Fourier transform. Once you do the Fourier transform, then you get basically, I mean, you see, I mean, this is just the sum over the eigenvalues, and this is just a trace of the propagator square. So that is very simplified analysis. I mean, there are many details I'm not discussing here, but you'll see later for quantum spin systems, this can be done precise. I'm just wanting now to give you a flavor of how this looks. So, I mean, then there was this, I mean, this picture is again copied from an old review paper by Berry, just showing, I mean, this is the typical structure of the spectral form factor. So the spectral form factor is a Fourier transform of the two-point spectral correlation function. So its natural scale is a time. Yeah? The spectral two-point function has a scale which is energy, and the Fourier transform is time. And then there's a particular time scale which is scaled to 1 here, which is the Heisenberg time. So in random matrix theory, the spectral form factor is growing linearly, and then it saturates, and then it has a plateau. So the key feature of random matrix theory is encoded in this linear growth of spectral form factor. When you have a model which is not integrable, which is integrable, which is not chaotic, then the spectral form factor is just flat. It has no structure as a function of time. So you want to understand why dynamical systems exhibit this linear ramp of spectral form factor. Yeah? And well, that's basically the key question. Yeah? So now this question has been answered in chaotic systems using semi-classical analysis. Yeah? And I will just flash the main argument, which is the so-called diagonal approximation by Berry. So assume as I argued, that quantum propagators can be using Feynman path representation of the time evolution, and then doing stationary phase approximation, you arrive at the sums over periodic trajectories. Yeah? So I mean, trace of u to the t is a trace of the propagator, so you only should take care of trajectories which are periodic, which come back to the same point in phase space. So basically, you can think of each u to the t, a trace u to the t. I mean, basically, this was the form factor is trace of the propagator square. So each part, so it's a product of two terms. One is the complex conjugate of the other. So you have two sums of periodic orbits. And then Berry argued, using a very simple-minded random phase approximation, that in this horrible sum, which is actually divergent. I mean, these sums are very difficult to manage mathematically, but still, using some sort of heuristics, theoretical physics heuristics, Berry argued that this sum actually basically reduces to a single sum of the so-called diagonal terms. I mean, that all of diagonal terms are vanishing due to random phase. So the diagonal terms are very easy. I mean, all these phases cancel, and it so happens that due to ergodicity, classical ergodicity, there is a sum rule, the so-called Hanai-Osorio-Almeida sum rule, which tells you that these sums are equal just to the length of periodic orbits. Here should be tau. I mean, tau should be length of the orbit. Yeah? So basically, you are summing over all periodic orbits of length tau, and this sum should be equal to the length of the periodic orbit. So we get basically increase due to ergodicity, due to classical ergodicity. So this was all the result of Berry, that the spectral form factor grows and the random matrix theory applies because of classical ergodicity. That was, I mean, of course, this is just the first term. There's lots of things missing, but that's the key. And then there's this factor of 2, which is kind of weak localization correction. It has to do with the fact that to each orbit, you also have the time reversed orbit, which couples in this double sum. So there are two pairs of orbits. To each orbit, there is the same orbit and the time reversed partner, which gives you the factor of 2. So that's the time reversal invariant case. And then there was the progress was very slow in this question, but 16 years later, there was a paper by Sieber and Richter, who basically then pointed out what should be the next term, because this was the leading term. I mean, the random matrix formula for form factor. I mean, now we are discussing time reversal invariant systems, and the form factor of let's say, the so-called orthogonal ensemble of random matrix theory has 2t, but then there are corrections. Then there is 2t square over t Heisenberg square plus higher order terms, t cube and so on. So this was just the first term. And then the second term was related to this number, to these orbits, to the set of orbits, which is small but is contributing to the next order, which are encountering themselves, which come close to themselves, and so they can be reconnected. They can be argued that they come in doublets because when orbits come close to itself, there could also be an orbit where this orbit doesn't go like number 8. I mean, doesn't go like this, but it crosses, not crosses because this is phase space, but it goes in the other way. So there are two possible reconnections of the orbits when they come close to themselves, which means that they're actually doublets of orbits. I mean, they are kind of precise arguments, which has been developed by Ziegler and Richter, which show that the orbits should come in pairs. And then there was basically PhD thesis of Sebastian Miller, which basically completed this question, doing the full combinatorics, and basically they argued that the whole series should be exactly the result of random matrix theory. So that was a really beautiful result because it connects semi-classical analysis to random matrix theory, which at first sight have nothing in common. Okay, so that was the state of the art of single particle problem. Yeah? But now we have a many body problem. So, and then there is a lot of data from many body problem, like even in the beginning of 90s, I mean, to my knowledge, the first data were in this paper of Montambo and company in 93. And then, people got used to this data. So then you read papers like, they say, okay, this model has Wigner-Dyson statistics, has Wigner spacing distribution, so it's chaotic. I kind of developed sort of, I kind of got nervous whenever I saw this kind of statements because, it is just, using this as a definition of quantum chaos, but nobody understood what quantum chaos means in this type of models. Yeah? So why on earth, you have this very simple model, like take this TV model, you have this one-dimensional model of fermions, spinless fermions, which have two hopping terms and two interaction terms with nearest neighbors and next nearest neighbors. So if there are no next nearest neighbor terms, this model is exactly integrable. It's equivalent to Heisenberg XXZ Hamiltonian. But when you switch on these terms, then the model is non-integrable, and then it displays a nice Poisson to Wigner transition. Yeah? This is from the paper from a review paper by Marcos Rigol and Lea Santos. But as I say, this type of, this was 2010, but there was a lot of numerics also by myself on many different models showing this type of transitions. And the question is now in my talk is just how can I understand Wigner for non-integral model? Okay, so now my talk somehow begins. So now I would like to maybe just derive for you a very simple result. Forgive me of being a little bit formal here, but since the result is so simple, I think I can be formal because just to show you what is the key features. But the model is very simple. We will try to now come up with the simplest model for which we can derive random matrix spectral form factor. So a kind of minimal model of quantum chaos. Actually, there will be models of two types. I hope my time of 30 minutes will permit to show you both. But let me just start with a more general model, which is, first of all, this is a kicked model. So it's a Floquet system, really. The reason being that kick systems are somehow easier for, let's say, from dynamical systems perspective, because there is no Hamiltonian, there is no conserved quantity. So one does not need to sit on the energy shell. One just can average over the full quasi-energy range, which is from 0 to 2 pi. Right, so there is no energy dependencies. Okay, so this is the Hamiltonian. It's time dependent. It's kicked. So there is H0. There is a free part, and then there is a kicking part. The free part is just classical Ising Hamiltonian. So I will just take I will simply here think of completely general Ising Hamiltonian with some longitudinal field, with some Ising interaction, which is two-body, plus maybe higher body interactions. I will also not specify anything on the range of interaction. I will argue later my range has to be slightly long-ranged. Reasons will be discussed. But I will not introduce any, also I will not discuss any randomness here, any disorder. I will actually pick up some very specific parameters, which have very kind of, just 1 or 2 or 3 parameters. Yeah? Because, one of the intuitive reasons why I want to do that is also not to use any sort of disorder averaging, but just try to do it for a clean system. Because, eventually we have to do some sort of averaging, but this averaging should be kind of minimal averaging. Yeah? Okay, so this is the free part, and the kicking part will be simply transverse field, which is the most orthogonal to the free part, somehow. We'll see what it means. So now, this is the the Hamiltonian, and this Hamiltonian corresponds to a Floquet operator, which is just propagator after one period of the drive, which is 1. I decompose it in V times W. So V times W are two unitaries, which are the exponentials of two parts of the Hamiltonian. One is diagonal in this spin basis, and the other is, well, again, very simple. It's just a pure tensor product of 2 by 2. So it's basically, this is a e to the IH sigma x Pauli matrix, and this you do tensor L sides. My curly L is the system size. This has to do with the fact that you have this, I mean, yeah, well, you see what I mean. So this is a sort of a generalized variant of the so-called Kick-Teasing models that I've been also playing around for almost 2 decades. Mainly numerically, but these models are kind of super easy to do computations. I mean, at least if you want to do exact computations, are very easy. You don't have to do any trotterization. I mean, you can very efficiently code this type of tensor products in your classical computer. So you can do systems of, let's say, 20, 24, 25, whatever spins, but not more than 30, of course, not even more than 24, I think. Anyway, so now let's see how you can calculate spectral form factor. So you remember, I have not yet showed you a precise definition, but precise definition was already here. I mean, spectral form factor is just trace of the propagator square and then expectation value with respect to something. So how should I calculate this? So, okay, so let me first start with the basis, which is, of course, I mean, I will now try to intuitively follow the same path as you follow semi-classically. I mean, first you identify the propagator, the trace of the propagator with some sort of path integral representation. But now, of course, you have spin 1/2 system, so there should be path integral should be something like a discrete sum of exponentially many terms. But then, of course, you have to be able to control constructive interferences in this many-body sum. Now, when you have stationary phase approximation, this is very clear how to do. But when you have a discrete sum, it's not so clear. But so happens, as you will see, I'll try to convince you that here statistical mechanics helps us. That you can map this problem to a very standard problems in statistical mechanics. And you see that basically this contributes constructively. I mean, this corresponds to constructive interference in these double sums, which I will be discussing later. So let's first pick up the basis. So the basis is a standard classical spin basis. So it's an eigenbasis of sigma z. So these s's are numbers which are 0 or 1. 0 corresponds to spin up and 1 corresponds to spin down. And so this W is diagonal operator, which is a pure phase, which is a pure multiplicative phase. So when this W acts on a computational state, it just basically replaces it by e to the I phi, where I phi is this classical, if you want, this classical Ising energy, yeah? Times the I. I mean, the I is there. Okay, and then the other operator is also very simple in this computational basis. Its matrix elements are pure products. Right? This has to do with the tensor product structure. So if you evaluate the matrix element into two arbitrary computational basis states, it's just a product of 2 by 2 matrix elements. Yeah? And now we are kind of ready to write the full-fledged spectral form factor. Yeah? It looks at this point as a horrible double sum, right? And basically what you do is, this is the definition. This is trace of u to the t square. I write it as trace of u to the t, trace u to the t star, which is complex conjugate. And then you do some sort of averaging. So I will have to argue what kind of averaging I mean. But usually, this object is not self-averaging, as is known in random matrix theory. So one has to average either over a short range of time or over a small ensemble of systems around some particular system that you're interested in, or over some single one parameter in the model, but still it has to be averaged over something. Otherwise, it's all over the place. So I will still keep some sort of averaging here. And now this is this double, this product of 2u to the t, then I basically replace it by double multiple sums, where each multiple sum is obtained by inserting identity, because this is u to the t, so to each u, between each powers of u, I insert identity, and the corresponding classical spin variable I denote as s sub t. So it's like a trajectory. It's like what you do when you open Feynman Hips on the first page, on the first or second chapter, you basically have this, right? You just insert position basis, now you insert spin basis. You arrive to something which reminds us of a discrete path integral. Yeah? But it has two contributions. It has this kinetic contribution and potential contribution. Yeah? And now I will keep the averaging over the kinetic contribution because I argue now these phases should somehow be, random enough. Now I have phases. You see, these phases are extensive. They are, and I'm interested in large quantum systems. These phases are extensive, so my argument will be that these phases go around unit circle many times. So when I try to average, basically I can say something if I just assume that they are pseudo-random. So this will be the key here, right? So we have this double sum of the phases times the double product over space and time of these two by two matrix elements. We just have two values. I mean, just to remind you, it's two values are cosine magnetic field and I sine magnetic field. So this is the key. The magnetic field, the transverse magnetic field, is the key parameter. Once it's 0, the model is integrable. When it's large enough, the model becomes chaotic. Yeah. Okay, so that's the key, and then you just have to basically accept the main assumption. At this point, you have to accept this assumption, and then we can comment later what does it imply, accepting the assumption. So this assumption is that once you do the averaging over this double sum of the phases, you have to pick up the delta, and the delta fixes that this set of phases should be equivalent to this set of phases, modulo ordering, because there is a sum. So basically, this set of phases corresponds to a trajectory, and this set of phases corresponds to a partner trajectory, and you want to couple these two trajectories, and this delta tells you that the collection of the phases should be the same up to permutations. Assuming that none of the phases repeats, but there is 2 to the L possible configurations, and the time should be short with respect to 2 to the L, which is the Heisenberg time. So for times much shorter than the Heisenberg time, probability of repetition is small. So that should be our first Berry's diagonal contribution. I will discuss the rest later, but let me just make this assumption here, namely assumption on non-repeating phases. Non-repeating configurations means that there has to be a permutation which flips the trajectory, the trajectory S of t to the trajectory S prime of t. So by this pi of t, I mean a permutation of t things. So then, after accepting this, I can simply rewrite my spectral form factor as a sum over all possible permutations, and then for each fixed permutation, this horrible double sum basically over space and time maps to a power of a sum over time, only over trajectories of a single spin to power L. So sorry, you should look at this one. So this gives you a delta. So then this gives you basically a single kind of partition function. I mean, I will now comment on this object, and this is like a partition function of a classical 1D statistical model. And this has to be done to power L. So now this multiple sum is just powering L. Yeah. So that's a huge simplification of the problem. And the reason being this random phase approximation, which is equivalent to Berry's random phase in semi-classics. Yeah? So that's the first term. But since we were completely blind, this gives us the first kind of hint where is what's the mechanism of having RMT in many body systems. Okay, so accepting this, so now we can ask ourselves, I mean, okay, this is still a sum over 2 to the S t factorial terms, right? There are t factorial permutations, but some are more important than the others. But moreover, I mean, you have also here the capital L, I mean, to power L, and this power L means that, when you go to thermodynamic limit, and you should probably do the thermodynamic limit before, at least it's more important, so you should first think of doing limit L to infinity. And this means that, as soon as there is a gap in this distribution of these partition functions, if one is larger than the other, then the others will give us exponentially small contributions. So now we just have to identify the leading contribution, sort of the permutation for which this partition function. This partition function looks like a partition function of some sort of twisted classical 1D Ising model, right? I mean, you have a periodic string of these two-body matrix elements multiplied by a twisted string. I mean, so basically you have a ring, and then you have a partner ring in which you just scramble the phases, scramble the spins. And then you have here nearest neighbors, but here you have, the guys which are all over, they're connected all over the place. But there are special permutations which map nearest neighbors to nearest neighbors, which will give us leading contribution because they give us constructive interference here. And these permutations is identity, all the cyclic permutations, and the reflections composed with cyclic permutations. So they're exactly symmetry groups of regular polygons of T vertices or dihedral group. So we have exactly 2D permutations which give us leading contribution. So once you prove, and I will try to just show you how we prove that the rest is strictly smaller, but once you are able to show that the rest is strictly smaller, you have immediately the leading contribution in thermodynamics to spectral form factor, which is just 2 times t, which is the number of terms which are dominating, times each term, but each term is just now this really becomes the standard textbook partition function of classical 1D Ising model, yeah? Which can be computed in terms of 2x2 transfer matrix, which is just 1 plus cosine 2h to power t. And then everything to power L. Now, if you do, then now one has to study, I mean, this in different regimes. One has to scale system size to infinity and also take maybe large times, right? Because, you know, I forgot to discuss that, but probably it's anyway too many things, and I should probably just keep some under the rug. But it's kind of easy to discuss that in this once you arrive to here. Namely, there is times which are usually denoted as Ehrenfest times in semi-classics or as Thouless times in disordered systems, below which random matrix theory should not apply. And now you see, I mean, here also we have some natural times below which random matrix theory doesn't apply. So you see, I mean, for times much larger than T star, which is easily deducible from here, which is scaling as log L divided by log cosine 2h, which is a strictly positive number because cosine h is strictly less than 1. And it's some fixed number. So but this time scales like log L. I mean, okay, this is negative, but there is minus, so it's positive. So, so there is a nice kind of crossover time, which is scaling as log system size, above which we get this random matrix behavior, and below which we have non-universal behavior. Okay, so maybe this is basically the end of the sort of the discussion of this very simple basic mechanism. So is there any question? Maybe interrupt me here. Otherwise, I show you some results. I mean, how does this work? So, yeah.
You have a log of a cosine. Cosine was negative?
Yeah, I mean, cosine is, I mean, this is log of the cosine is negative, but there is a minus here, I mean, so it's positive.
No, the cosine itself could be negative.
Okay, so cosine could be negative, yes, you're right. I mean, here I assume that cosine is positive, otherwise, you know, otherwise actually it's a very interesting question. I completely forgot, but then you get sort of, you know, then you get some sort of quasi-crystal, right? Because you have the spontaneous breaking of, I mean, then you have some form factor which actually displays oscillations, period 2 oscillations, right? So because you get complex logarithm, right? It gives you a phase, right? But then, I mean, I wanted to not to mention that, but thanks for asking. Okay. So yeah, but you see, I mean, we derived this first term in the random matrix description. Now let's see how we can move on. So actually, I guess, how am I doing with time? Because maybe I can. 8 minutes more. Okay, so I think I will. Okay, I just, you know, some slides I will just go through because I want to show you also the last slide, which I find most exciting, and the questions. Yes, so including, yeah. So I'll try to finish in 4 or 5 minutes. So this is just one slide which I invite you to read the paper on the archive in case you're interested. But this is just a slide to show you that these partition functions are actually, they have a gap. So that there is a correction. I mean, there is, you know, there is exponentially small corrections to the term I showed you before. And there is a diagrammatics which allows you to compute these corrections. And so basically, it's a natural, one can order these permutations very naturally. For example, the leading order are permutations which conserve the neighborhood. So they map circle to a circle. But then the next order are permutations which make one cross. So for example, they map a circle to almost a circle, and then they exchange two neighbors across. And so they make a single X. We call this a single X diagram. And then the next order are permutations which have two crosses, two X diagrams, and so on. So you can show that in thermodynamic limit, I mean, they have a larger and larger gap with respect to the Ising partition function. So they are basically strictly smaller. And then doing again, going back to our key assumption that these configurations were not repeating, then you can ask yourself, I mean, but what about if I take into account also repeating interactions? Then you find that you have overcounted some terms, you have to subtract them. And what you have to subtract is exactly second order in random matrix theory. So that's also something that you can do it systematically exactly. And that's also in appendix of a paper. But the rest is left to future. So I guess the rest of diagrammatics is again following PhD thesis of Sebastian Miller, but translating it to a discrete language. Okay. So now just give you some results, some numerics. So I mean, to show you that this works for a very simple model. So we choose a model which has these simple coupling parameters. We take longitudinal field, which has some, we have to break all the symmetries. So we have to break left-right symmetry because the trivial geometric symmetries we don't want to have. So we broke left-right symmetry by introducing one particle field which scales from one end. Let's say x is the position from the left end with some power alpha. And then we also take this two-body coupling, which has some scaling, which is some power law scaling. So we take this long-range Ising model with some long-range exponent, which is certainly larger than mean field. So we don't want to have mean field physics, but we also don't want to have very short-range physics. I mean, we would like to have, but this theory will then just stop working because then our random phase approximation doesn't work. Our extensivity of phase is not pseudo-random. I mean, our extensive phases are not pseudo-random enough. So I mean, I can discuss all that in private because I have to hurry, but I mean, these are things which I can argue. And then once you have this phase alpha, this exponent alpha between, let's say, 0.5 and 2 or 2.5, then these things will work nicely. Okay, so then what I show in the first plot now is the integrated spectral form factor, integrated in time, so some kind of cumulative spectral form factor, which we did in order to basically overcome the problem of self-averaging, because we are not we are now not averaging over anything. We just take a fixed model, and this is what we get. So this is integrated spectral form factor. These bullets, colored bullets are numerics for particular transverse magnetic field. So 0 means integrable, so you have nice Poisson. And this is just Poisson, which is now linear because it's integrated constant. And now random matrix is like quadratic, right? This is log-log scale. So you see this would be the full curve would be RMT, the exact RMT. The dashed would be our random phase model. And this dashed would be our random phase models at these different parameters h. And the bullets would be our numerics. So you really probably agree that this is a very nice agreement. Yeah? Now, without doing the integration, then you have to do some averaging. So for example, in this plot, we compare results with finite time averaging, where we take moving time averaging over 10 points in time. And then we compare these to 10 sample averaging. So we take 10 different realizations of the model with 10 different J parameters, and we average those. And this one is blue, and the other is orange. You see that basically they oscillate around the same random phase model curve. This is not RMT exactly. RMT is only in the limit of large times. But this small time regime is exactly the model, our theoretical model that I have shown you before. Okay, I have to just keep some details. For example, the last figure of this model is also comparing different parameter alpha. So this alpha, you see, this is basically some order parameter which tells you how close you are to RMT. If you are in the gray band, you are basically you're not RMT, but the random phase model, the model that is RMT in the large time. But it's basically a solution of our problem I discussed before. But you see, in the gray band, it means somehow we agree with the model, and then when alpha is too large, means we are in short-range physics, then basically we deviate too much. And when alpha is too small, we are in mean field physics, we also deviate. But between 0.5 and 2.5, I don't know, maybe 2 is the right critical value. This is just numerics, but we somehow have good agreement. Okay, so now I wanted to conclude. I almost concluded, but I would like to show you one more slide. So now, this kind of, to me, was very satisfactory because I have seen the first kind of mechanism which indicates why random matrix theory works in simple models of many-body spin systems. But there were kind of few points which we wanted to understand better. One was this pseudo-randomness argument. And the second, which is somehow related, is what happens when you have strictly local interactions, alpha to infinity. And this is something which has to be understood separately. And then there are various other things you can do with the same method, but which will have to be done in future. And among other things, which I found personally most exciting, is that one could probably be able to say something about more, let's say, more quantitative or more rigorous on why ETH holds in non-integrable systems and so on. But let me just, if I have 1 minute. No. I probably will lose my questions, but okay. So let me just give you one slide because this is a progress of, let's say, last week. Progress of last month, but it has been put on the archive last week. So, why am I, you probably noticed that I'm quite excited about this, but this is something which made me even more excited because, it's something that we were able actually to show with some mathematical rigor. Namely, for a model which has exactly local interactions, which is this model, which is the same version, but just now strictly local interactions. Now I put some position-dependent longitudinal field with some disorder if you want, but this disorder will be removed at the end. For that model, we can somehow prove that one has a random matrix spectral form factor in thermodynamic limit. So in thermodynamic limit, Heisenberg time moves away to infinity. So the only thing you have to prove is that form factor goes as 2t, right? Because model has TRI. So, and this is, and our proof only works so far only for odd times. For even times we have conjecture, but for odd times we have a proof, and the proof is based on some sort of tensor network description of this Spector form factor, which is depicted in the figure. I have no time to comment. With this, I would like to close, and thank you for your attention.